April 24th, 1943, 174, Tunisia. The silence that followed the last German radio transmission was broken only by the sound of British boots crunching across North African gravel. Lieutenant Colonel Derek Lidderdale of the Royal Tank Regiment approached the abandoned German heavy tank with a mixture of professional curiosity and genuine unease. The massive vehicle sat motionless on the hilltop, its 88mm gun barrel still pointed toward the valley, where British Churchill tanks had fought desperately for 2 days. What Lidderdale was looking at represented something unprecedented in Allied experience. A Tiger tank, largely intact, abandoned by its crew after sustaining damage that left it immobilized but not destroyed. The Wehrmacht had intended to recover or demolish this machine, but the rapid British advance had prevented both options. Now, for the first time in the war, Allied forces possessed a complete example of Germany's most feared armoured weapon. What neither Lidderdale nor his men understood in that moment was that this single abandoned tank would trigger the most comprehensive technological assessment in British military history. The lessons learned from examining this machine would fundamentally alter Allied understanding of armour technology, metallurgy, and weapons design. The British engineers who would spend the next 2 years dissecting every component of this tank would eventually reach a conclusion that challenged everything they believed about their own technical capabilities. They had captured not just a weapon, but evidence of German engineering superiority that exceeded their most pessimistic estimates. The story of how British technical experts came to acknowledge German technological dominance begins not with the capture itself, but with the profound ignorance that preceded it. The Tiger tank that sat abandoned on Point 174 had been in combat for only 7 months, making its capture one of the earliest opportunities for Allied forces to examine German heavy tank technology. The timing was crucial because the Tiger represented a revolutionary leap in armoured vehicle design that Allied intelligence services had struggled to understand through fragmentary battlefield reports and blurry reconnaissance photographs. British tank crews had been encountering these machines since late 1942, returning with accounts of German armour that seemed impervious to their guns and German firepower that could destroy Allied tanks at ranges previously considered impossible. The mathematical reality of Tiger encounters was stark and disturbing. British tactical doctrine had established that 5 Sherman tanks were required to engage a single Tiger, with only 1 Sherman expected to survive the encounter. This 5-to-1 loss ratio represented a technological disadvantage so severe that it challenged fundamental assumptions about Allied industrial and engineering capabilities. Yet despite mounting battlefield evidence of German superiority, British engineers had no opportunity to conduct systematic analysis of the enemy technology until Tiger 131 fell into their hands. The recovery operation itself revealed the extent of British unfamiliarity with German engineering. The tank weighed 64 tons, nearly double the weight of contemporary British designs, requiring specialised equipment and procedures that Allied forces had not previously needed. The damage that had forced the German crew to abandon their vehicle was relatively minor by combat standards. A freak hit had buckled the roof over the driver's position and jammed the turret traverse mechanism. Previous battle damage had made the gun elevation system sticky and unreliable. For German crews accustomed to the Tiger's mechanical complexity, these problems made the tank temporarily inoperable. For British recovery teams, even these damaged systems represented technology they had never encountered. The electrical systems alone were more sophisticated than anything British engineers had installed in their own tanks. The transmission, manufactured by Maybach to tolerances that exceeded British production capabilities, demonstrated precision engineering that British designers associated more with aircraft than with ground vehicles. The journey from battlefield capture to technical analysis revealed British recognition that they were dealing with something extraordinary. Tiger 131 arrived at Liverpool docks in October 1943, having been shipped directly from Tunisia for detailed examination. The decision to transport the entire tank to Britain rather than conducting field analysis in North Africa reflected the priority that British intelligence placed on comprehensive technical assessment. The vehicle was immediately transferred to the School of Tank Technology at Chobham in Surrey, Britain's premier facility for analysing enemy armour technology. The School of Tank Technology had been established specifically to provide systematic analysis of captured equipment, but Tiger 131 represented the most significant intelligence windfall the facility had ever received. British engineers finally had the opportunity to examine German heavy tank technology under controlled laboratory conditions, with access to the most sophisticated testing equipment available to Allied forces. The initial examination of Tiger 131 by British technical experts began with careful external inspection that revealed manufacturing quality exceeding their expectations. The welding throughout the tank's structure showed consistent penetration and minimal defects, demonstrating production standards that British engineers acknowledged as superior to their own methods. The armour plating itself exhibited surface finish and dimensional accuracy that reflected more sophisticated manufacturing processes than British factories typically employed. Even in its battle-damaged condition, the Tiger demonstrated attention to detail in component manufacturing that British engineers found impressive. The precision evident in seemingly minor components suggested German manufacturing capabilities that extended far beyond what Allied intelligence had estimated. The optical equipment alone, including the sophisticated range-finding systems integrated into the tank's fire control, represented technology that British engineers had not encountered in their own designs. The discovery that German tanks employed such advanced fire control systems forced British technical experts to reconsider their fundamental assumptions about enemy capabilities. The systematic disassembly of Tiger 131 began in November 1943, with British engineers approaching the task like archaeologists examining an alien artifact. The preliminary report released that month represented only the beginning of an exhaustive analysis that would continue for more than 2 years. Every major system required careful documentation and testing to understand German design philosophy and manufacturing techniques. The engine, a sophisticated Maybach unit producing 700 horsepower, demonstrated German advances in automotive engineering that British designers had not anticipated. The transmission system employed gear ratios and control mechanisms that reflected understanding of mechanical engineering principles that British tank designers had not fully explored. The suspension system, utilizing interleaved road wheels and torsion bars, provided ground pressure distribution and ride quality that exceeded anything in British service. Each component revealed German engineering solutions that British designers acknowledged as more advanced than their own approaches. The armour analysis conducted by British metallurgists provided the most shocking revelation of the entire Tiger 31 examination. British testing determined that German 80mm armour plate provided protection equivalent to 92mm of British steel, representing a 15% advantage that could not be explained by thickness alone. The German armour employed chromium-molybdenum alloy compositions that British manufacturers had not fully developed, combined with heat treatment processes that achieved superior hardness while maintaining adequate toughness. British metallurgical analysis revealed that German armour steel incorporated alloying elements in proportions that British industry had not systematically explored. Chromium content in German armour could reach 2.5%, while molybdenum ranged from 0.5% to 0.75%. These alloy compositions, combined with more sophisticated heat treatment procedures, produced armour that maintained optimal ballistic resistance, while avoiding the brittleness that plagued some British armour designs. The discovery that German metallurgy had achieved such superior results forced British engineers to completely reconsider their own approaches to armour development. The examination of the Tiger's main armament system revealed German achievements in weapons technology that British engineers found even more disturbing than the armour superiority. The 88mm KWK-36 gun represented a quantum leap in tank armament that exceeded British capabilities by a significant margin. British firing trials conducted with the captured weapon demonstrated accuracy that British tank guns could not match. 5 successive hits were scored on a target measuring 16 by 18 inches at a range of 1,200 yards, demonstrating precision that British gunners had never achieved with their own weapons. The penetrating power of the German gun was equally impressive, capable of defeating all contemporary Allied armour at ranges exceeding 2,000 metres. British tank guns required engagement distances of less than 500 metres to have any realistic chance of penetrating Tiger armour. The ammunition employed by the 88mm gun incorporated metallurgical advances that British ordnance experts had not developed, including armour-piercing rounds with superior penetrating performance and explosive effectiveness. The integration of the Tiger's weapons systems demonstrated German advances in fire control technology that British engineers acknowledged as years ahead of their own capabilities. The optical range-finding equipment employed sophisticated lens systems and precision manufacturing that exceeded British optical industry standards. The gun mounting system within the turret incorporated recoil management and stabilization technology that contributed significantly to the weapon's accuracy. British engineers discovered that the Tiger's fire control systems were designed as integrated units rather than collections of separate components, reflecting German understanding of weapon system engineering that British designers had not fully developed. The electrical systems supporting the fire control demonstrated reliability and sophistication that British engineers found superior to their own approaches. The discovery that German tanks employed such advanced integrated weapons systems forced British technical experts to acknowledge that enemy engineering capabilities exceeded their own by a significant margin. The mechanical systems analysis revealed German automotive engineering achievements that influenced British tank development for decades afterward. The Tiger's transmission, while complex, demonstrated precision manufacturing that British engineers found superior to their own methods. The final drive assemblies were manufactured to tolerances that exceeded British production capabilities, resulting in durability and performance characteristics that British designs had not achieved. The cooling systems employed thermal management principles that British engineers incorporated into subsequent tank development programs. Even the electrical architecture demonstrated integration and reliability that influenced British approaches to vehicle electrical systems in later designs. British engineers recognised that German mechanical engineering had achieved a level of sophistication that their own industry had not reached, forcing comprehensive re-evaluation of British tank development priorities. The broader implications of the Tiger 131 analysis extended far beyond immediate tactical concerns, fundamentally altering British understanding of the technological balance between Allied and Axis capabilities. British engineers realised that their traditional emphasis on reliability and ease of production had resulted in designs that were inadequate when confronted with German technological superiority. The Tiger represented evidence that German engineering had achieved advances in multiple critical areas simultaneously, creating weapons systems that exceeded Allied capabilities by margins that could not be overcome through minor modifications or incremental improvements. The analysis forced British designers to acknowledge that fundamental changes in their approach to tank development would be required to compete effectively with German technology. The comprehensive nature of German superiority demonstrated through Tiger 131 examination influenced British industrial policy and resource allocation for the remainder of the war. The quality control procedures evident throughout Tiger 131's construction challenged British assumptions about German industrial capabilities under wartime conditions. British engineers had expected to find evidence of declining manufacturing standards as Germany faced increasing resource shortages and production pressures. Instead, the detailed examination revealed precision engineering that exceeded peacetime British standards. The dimensional accuracy of machined components suggested German factories maintained quality control procedures that British industry had not implemented. Surface finishes on critical wear components demonstrated manufacturing processes that British engineers acknowledged as superior to their own methods. The consistency of welding quality throughout the tank structure indicated German welders possessed skills and training that British production lines had not achieved. Even consumable components like gaskets and seals showed material quality that British suppliers had not matched. This discovery forced British industrial planners to confront an uncomfortable reality. German manufacturing capabilities remained sophisticated despite 2 years of strategic bombing and resource constraints. The ammunition storage and handling systems within Tiger 131 revealed German innovations in internal layout design that British tank designers had not considered. The arrangement of main gun rounds demonstrated understanding of combat loading procedures that British engineers found superior to their own approaches. German designers had optimized ammunition placement for rapid loading while maintaining crew safety standards that British tanks had not achieved. The storage racks themselves employed materials and construction techniques that provided better protection against secondary explosions than comparable British systems. British testing revealed that German ammunition handling procedures reduced loading time significantly compared to Allied methods. The discovery that German tank interiors were designed with such attention to combat efficiency forced British engineers to reconsider their own approaches to vehicle layout and crew ergonomics. The integration of ammunition systems with fire control demonstrated German understanding of operational requirements that British designers had not fully appreciated. The examination of Tiger 131's communication equipment provided British signals, intelligence with unprecedented insight into German radio technology and battlefield coordination capabilities. The radio systems employed frequency ranges and transmission power that exceeded standard British tank communication equipment. The antenna systems demonstrated German advances in mobile communications that British signals engineers had not anticipated. British testing revealed that German radio equipment maintained reliable communication at ranges that exceeded Allied capabilities by significant margins. The quality of German electronic components suggested manufacturing capabilities in precision electronics that British industry had not achieved. The integration of communication systems with vehicle electrical architecture demonstrated German understanding of electronic engineering that British designers acknowledged as more advanced than their own approaches. The discovery that German tanks possessed such sophisticated communication capabilities forced British tactical planners to reconsider their assumptions about enemy coordination and command effectiveness. British metallurgists conducting detailed chemical analysis of Tiger 131's steel components discovered German achievements in materials science that challenged fundamental assumptions about Allied technological leadership. The steel compositions employed throughout the tank's structure incorporated alloying elements in combinations that British metallurgy had not systematically explored. Vanadium content in critical components reached levels that British steel producers had not attempted in production quantities. The heat treatment procedures evident in examined components achieved hardness gradients that British manufacturing had not mastered. Microscopic examination revealed grain structures that indicated German steel processing employed more sophisticated temperature control than British methods achieved. The discovery that German metallurgy had developed such advanced materials forced British steel industry leaders to acknowledge significant gaps in their own technical capabilities. The implications extended beyond tank production, affecting British understanding of German capabilities across all steel-dependent industries, including aircraft and naval construction. The hydraulic systems analysis revealed German fluid power engineering that exceeded British expectations in both sophistication and reliability. The power steering mechanisms employed hydraulic principles that British automotive engineers had not fully developed for military applications. The filtration systems demonstrated German understanding of fluid contamination control that British hydraulic designers had not implemented. British testing revealed that German hydraulic components maintained performance specifications under temperature and pressure conditions that exceeded the operating envelope of comparable British systems. The precision manufacturing evident in hydraulic pumps and valves suggested German capabilities in close tolerance machining that British industry had not achieved in production quantities. The integration of hydraulic systems with mechanical components demonstrated German engineering philosophy that emphasized system optimization rather than component optimization. The discovery that German engineers had achieved such advanced hydraulic integration forced British designers to reconsider their own approaches to power transmission and control systems. The detailed examination of Tiger 131's tracks and running gear provided British engineers with insight into German understanding of ground mobility that challenged Allied assumptions about tracked vehicle design. The track construction employed materials and manufacturing techniques that achieved durability characteristics exceeding British track designs by significant margins. The rubber compositions used in road wheel tyres demonstrated German advances in synthetic materials that British chemical industry had not developed. British testing revealed that German track systems maintained performance characteristics under conditions that would cause British tracks to fail. The sprocket and idler wheel designs incorporated wear compensation features that British engineers had not implemented in their own designs. The discovery that German tracked vehicle technology had achieved such superior performance forced British mechanical engineers to acknowledge fundamental gaps in their understanding of ground mobility systems. The implications affected British development programs for all tracked vehicles, including tanks, self-propelled artillery, and specialized engineering equipment. British engineers conducting thermal analysis of Tiger 131's engine cooling systems discovered German achievements in heat management that influenced Allied engine development for decades afterward. The radiator designs employed heat transfer principles that British automotive engineers had not fully explored in military applications. The fan systems demonstrated German understanding of airflow management that exceeded British capabilities in cooling system design. British testing revealed that German cooling systems maintained engine operating temperatures within optimal ranges under conditions that would cause British engines to overheat. The materials employed in cooling system construction showed resistance to corrosion and thermal stress that British metallurgy had not achieved. The integration of cooling systems with engine management demonstrated German engineering philosophy that emphasized thermal efficiency as a primary design criterion. The discovery that German thermal management had achieved such superior results forced British engine designers to fundamentally reconsider their approaches to cooling system development and integration. The comprehensive nature of German technological superiority revealed through Tiger 131 analysis forced British engineers to confront uncomfortable questions about Allied industrial and scientific capabilities. The systematic examination had revealed German advantages in metallurgy, mechanical engineering, hydraulics, electronics, optics, materials science, and manufacturing processes. These advantages were not isolated achievements in specific areas, but represented comprehensive technological leadership across multiple disciplines simultaneously. British technical experts realized that German engineering had achieved a level of integration and optimization that Allied industry had not approached. The implications extended far beyond tank development, affecting British understanding of the overall technological balance in the war. The analysis suggested that German scientific and engineering capabilities had been systematically underestimated by Allied intelligence services and industrial planners. The psychological impact on British engineers conducting the Tiger 131 examination was profound and lasting. Many had spent their careers confident in British technological leadership and industrial superiority. The systematic discovery of German advantages in area after area forced fundamental reconsideration of professional assumptions and national capabilities. Senior engineers who had dismissed earlier reports of German technological superiority were confronted with undeniable physical evidence that challenged their entire understanding of the technological war. The detailed analysis revealed that German achievements were not isolated innovations, but represented systematic advances across multiple engineering disciplines. British technical experts found themselves in the uncomfortable position of acknowledging that enemy capabilities exceeded their own by margins that could not be explained by temporary advantages or wartime expedients. The recognition that German engineering had achieved such comprehensive superiority influenced British technical development priorities for the remainder of the war and well into the post-war period. The testing protocols established for Tiger 131 represented the most systematic approach to enemy technology assessment ever undertaken by British military engineers. The School of Tank technology developed comprehensive procedures that went far beyond previous captured equipment examinations. Each component required detailed documentation before disassembly, photographic records of manufacturing techniques, and systematic testing under controlled conditions. British engineers created specialised testing fixtures designed specifically for German components. Recognising that standard British test equipment was inadequate for evaluating superior enemy technology, the methodical approach reflected British acknowledgement that they were dealing with engineering achievements that required unprecedented analytical rigour. Traditional approaches to captured equipment assessment had involved cursory examination and rapid intelligence reports. Tiger 131 demanded comprehensive scientific analysis that would continue for years rather than weeks. The ballistic testing program conducted on Tiger 131's armour represented the most extensive penetration analysis ever performed by British ordnance specialists. The testing facility at Chobham constructed specialised firing ranges designed to evaluate German armour under controlled conditions. British engineers fired every available Allied anti-tank weapon against sections of Tiger armour, documenting penetration characteristics with scientific precision. The results were consistently discouraging. Standard British 2-pounder guns, still equipping many frontline tanks, could not penetrate Tiger armour at any practical engagement range. The 6-pounder guns that represented Britain's most advanced tank armament could only achieve penetration at ranges so close that survival was unlikely. Even the 17-pounder gun, Britain's most powerful anti-tank weapon, required optimal conditions and precise shot placement to achieve reliable penetration. The systematic testing confirmed battlefield reports that had seemed exaggerated or impossible. German armour technology had indeed achieved protection levels that rendered most Allied weapons ineffective. British metallurgists expanded their analysis beyond basic steel composition to examine German manufacturing processes that produced such superior results. The heat treatment procedures evident in Tiger 131's components involved temperature control and timing sequences that British industry had not mastered. German steel processing employed atmospheric control during heat treatment that prevented oxidation and maintained precise carbon content throughout the cooling cycle. British examination revealed that German furnace technology achieved temperature uniformity that British equipment could not match. The quenching procedures used in German armour production involved cooling rates and media compositions that British metallurgy had not developed. The tempering processes that followed initial hardening demonstrated German understanding of steel microstructure that British engineers acknowledged as more advanced than their own knowledge. The discovery that German steel processing had achieved such sophisticated control forced British metallurgical industry to acknowledge fundamental gaps in their technological capabilities. The detailed examination of Tiger 131's final drive assemblies revealed German mechanical engineering that exceeded British expectations in precision and durability. The gear cutting techniques evident in examined components achieved surface finishes and dimensional accuracy that British machine tool industry had not attained. British engineers discovered that German gear manufacturing employed cutting speeds and feed rates that produced superior surface characteristics without sacrificing dimensional precision. The bearing systems used throughout the final drives incorporated materials and manufacturing techniques that exceeded British capabilities in precision engineering. The sealing systems employed elastomeric compounds that demonstrated German advances in synthetic materials science. British testing revealed that German final drives maintained performance specifications under load conditions that would cause British systems to fail catastrophically. The lubrication systems incorporated filtration and cooling features that British automotive engineers had not implemented in military applications. The electrical systems analysis provided British engineers with comprehensive insight into German achievements in military electronics that challenged Allied assumptions about enemy industrial capabilities. The generators employed throughout Tiger 131 demonstrated German understanding of electrical engineering principles that exceeded British military applications. The wiring harnesses showed manufacturing quality and environmental protection that British electrical contractors had not achieved in production quantities. British testing revealed that German electrical components maintained performance characteristics under temperature and vibration conditions that exceeded the operating envelope of comparable British systems. The switching systems employed materials and construction techniques that provided reliability levels British military electronics had not attained. The integration of electrical systems with mechanical components demonstrated German engineering philosophy that emphasized system-level optimization rather than individual component performance. The discovery that German military electronics had achieved such advanced integration forced British electrical engineers to reconsider their fundamental approaches to vehicle electrical architecture. British optical specialists, conducting detailed analysis of Tiger 131's fire control systems, discovered German achievements in precision optics that exceeded Allied capabilities by significant margins. The rangefinder systems employed lens grinding techniques that British optical industry had not mastered in production quantities. The glass compositions used in critical optical elements incorporated materials that British glass manufacturers had not developed for military applications. British testing revealed that German optical systems maintained performance specifications under environmental conditions that would degrade British optics beyond acceptable limits. The mechanical precision evident in optical mounting systems achieved stability and accuracy that British precision engineering had not attained. The coating technologies applied to German lenses demonstrated understanding of optical physics that British researchers had not fully explored. The integration of optical systems with mechanical fire control components showed German engineering philosophy that emphasized total system performance rather than individual component optimization. The ammunition examination conducted by British ordnance experts revealed German achievements in projectile design that forced fundamental reconsideration of Allied approaches to anti-tank warfare. The armor-piercing rounds employed metallurgical techniques that achieved penetrating performance exceeding British projectile capabilities by substantial margins. The hardening processes used in German projectile manufacturing involved temperature control and alloy compositions that British ordnance industry had not developed. British testing revealed that German projectiles maintained structural integrity under impact conditions that would cause British rounds to shatter ineffectively. The explosive components incorporated materials and manufacturing techniques that provided superior blast effectiveness compared to Allied ammunition. The quality control procedures evident in German ammunition production achieved consistency levels that British manufacturing had not attained. The discovery that German ammunition technology had achieved such superior performance forced British ordnance specialists to acknowledge significant gaps in their own technical capabilities. The comprehensive assessment of Tiger 131's crew accommodation systems revealed German understanding of human factors engineering that British tank designers had not systematically addressed. The ergonomic design of crew positions demonstrated German analysis of combat effectiveness that exceeded British approaches to vehicle interior layout. British examination revealed that German crew stations provided operational efficiency advantages that British designs had not achieved. The environmental control systems maintained crew comfort levels that British tanks could not match under comparable operating conditions. The vision systems provided crew visibility that exceeded British capabilities in optical design and integration. The communication interfaces demonstrated German understanding of human-machine interaction that British designers had not fully explored. The discovery that German crew systems had achieved such superior integration forced British human factors specialists to reconsider their fundamental approaches to combat vehicle design. British engineers, examining Tiger 131's maintenance systems, discovered German approaches to field serviceability that challenged Allied assumptions about complex weapon system support. The component accessibility demonstrated German design philosophy that balanced performance optimization with practical maintenance requirements. British analysis revealed that German maintenance procedures achieved efficiency levels that British field service had not attained. The diagnostic systems provided maintenance personnel with troubleshooting capabilities that British service methods could not match. The tool requirements for German maintenance procedures employed specialized equipment that demonstrated manufacturing capabilities British industry had not developed. The training materials associated with Tiger maintenance showed German technical documentation standards that exceeded British military publication practices. The discovery that German maintenance systems had achieved such sophisticated integration forced British logistics specialists to acknowledge fundamental limitations in their own support approaches. The systematic comparison between Tiger 1 systems and contemporary British tank designs revealed technological gaps that extended across every major subsystem simultaneously. British engineers realized that German superiority was not limited to isolated innovations, but represented comprehensive advances in multiple engineering disciplines. The analysis demonstrated that German tank development had achieved integration levels that British design philosophy had not approached. Every system examined showed German capabilities that exceeded British performance by margins that could not be overcome through minor modifications or incremental improvements. The comprehensive nature of German technological leadership forced British engineers to acknowledge that fundamental changes in development approach would be required to achieve competitive capability. The recognition that German engineering had achieved such systematic superiority influenced British technical priorities for decades beyond the immediate wartime requirements. The intelligence implications of Tiger 1 analysis extended far beyond immediate tactical considerations to strategic assessment of German industrial and scientific capabilities. British intelligence services realized that their estimates of enemy technological development had been systematically incorrect. The systematic examination revealed German achievements that suggested research and development programs far more advanced than Allied intelligence had detected. The manufacturing quality evident throughout Tiger 131 indicated German production capabilities that contradicted Allied assumptions about wartime industrial degradation. The sophistication of German engineering solutions demonstrated scientific knowledge that Allied researchers had not anticipated. The comprehensive nature of German technological superiority forced British intelligence analysts to reconsider their fundamental assumptions about enemy capabilities and development timelines. British industrial planners examining the implications of Tiger HE-1 analysis faced uncomfortable questions about Allied production priorities and technological development strategies. The systematic German superiority revealed through detailed examination suggested that Allied industrial emphasis on quantity over quality had resulted in weapon systems inadequate for confronting German technology. The comprehensive nature of German engineering achievements indicated that Allied research and development programs had failed to maintain technological parity with enemy capabilities. British manufacturers realized that their production methods had not achieved the quality levels evident in German components. The discovery that German industry had maintained such superior standards under wartime conditions forced British industrial leaders to acknowledge fundamental limitations in their own manufacturing capabilities and development approaches. The long-term implications of British engineers' acknowledgement of German technological superiority through Tiger HE-1 analysis influenced Allied weapons development programs for the remainder of the war and well into the post-war period. The systematic examination had provided undeniable evidence that German engineering had achieved advances that Allied industry had not matched. British technical experts realized that competitive weapon systems would require fundamental changes in design philosophy and manufacturing approach rather than incremental improvements to existing systems. The comprehensive nature of German superiority demonstrated through Tiger 131 forced British engineers to abandon assumptions about technological leadership that had guided development programs since the beginning of the war. The recognition that German capabilities exceeded Allied achievements by such significant margins influenced British research priorities and industrial investment for decades afterward. The strategic ramifications of the Tiger 131 examination reached the highest levels of British government and military leadership, forcing uncomfortable conversations about the fundamental assumptions underlying Allied war strategy. Winston Churchill himself received detailed briefings on the technical assessment findings, confronting him with evidence that German engineering capabilities had been systematically underestimated by British intelligence services. The Prime Minister's private correspondence revealed his growing concern that Allied numerical superiority might be insufficient to overcome German technological advantages of such magnitude. Cabinet meetings throughout 1944 included increasingly frequent discussions of the technological gap revealed through systematic analysis of captured German equipment. British military planners realized that their strategic calculations had been based on flawed assumptions about relative technological capabilities. The comprehensive nature of German superiority demonstrated through Tiger 131 forced British leadership to acknowledge that victory would require not just greater production volumes, but fundamental advances in Allied technology that might take years to achieve. The educational implications of the Tiger 131 analysis transformed British approaches to engineering training and technical education throughout the war and beyond. Universities across Britain modified their engineering curricula to incorporate lessons learned from German technological achievements revealed through systematic examination of captured equipment. The metallurgical techniques discovered in Tiger armour became standard subjects in British materials science programmes. Advanced manufacturing processes evident in German components influenced British industrial engineering education for decades. Technical colleges established specialised programmes designed to train engineers capable of matching German precision manufacturing standards. The systematic examination of Tiger 1 had revealed gaps in British technical education that extended across multiple engineering disciplines simultaneously. British educators realised that German technical superiority reflected not just superior individual innovations, but comprehensive educational systems that produced engineers with more sophisticated understanding of integrated system design. British manufacturers, examining detailed reports from the Tiger 131 analysis, faced the sobering reality that their production methods had fallen behind German capabilities by margins that threatened long-term competitive viability. The precision manufacturing evident throughout Tiger components required machine tool capabilities that British industry had not developed. German heat treatment processes demanded furnace technology and atmospheric control systems that British steel producers had not implemented. The dimensional accuracy achieved in German machined components suggested quality control procedures that British manufacturers had not systematically adopted. Surface finishes on critical wear parts demonstrated German manufacturing techniques that exceeded British production standards. British industrial leaders realised that matching German technological capabilities would require comprehensive modernisation of manufacturing equipment and processes. The investment required to achieve competitive capability would extend far beyond wartime emergency expenditures to fundamental restructuring of British industrial capacity. The research and development implications of Tiger 131 analysis forced British scientific institutions to confront evidence that German research programs had achieved advances that Allied scientists had not anticipated. The materials science evident in German armour steel suggested research programs that had systematically explored alloy compositions and heat treatment procedures beyond the scope of British investigation. German optical systems incorporated lens, grinding techniques and glass compositions that indicated research capabilities British institutions had not matched. The precision engineering throughout Tiger components reflected understanding of mechanical principles that British researchers had not fully developed. Advanced manufacturing processes evident in German systems suggested industrial research programs that had achieved integration between theoretical knowledge and practical application. British scientific leaders realised that German research and development had achieved systematic advances across multiple disciplines that would require years of intensive investigation to duplicate or exceed. The psychological transformation experienced by British engineers through Tiger Hun T1 examination extended beyond professional acknowledgement of technical superiority to fundamental questioning of national technological identity. Engineers who had spent careers confident in British innovation found themselves confronting physical evidence that challenged their entire understanding of industrial capability and scientific achievement. The systematic discovery of German advances in area after area forced recognition that British technological leadership was more perception than reality. Senior technical personnel who had dismissed earlier reports of German superiority were compelled to acknowledge that enemy achievements exceeded their own by margins that could not be attributed to temporary wartime advantages. The comprehensive nature of German technological superiority demonstrated through Tiger 131 created lasting changes in British engineering culture that emphasised systematic analysis and continuous improvement rather than assumptions about inherent superiority. British testing facilities expanded their analytical capabilities specifically to accommodate the sophisticated examination requirements revealed by Tiger 131 analysis. The School of Tank Technology acquired specialised equipment designed to evaluate German manufacturing techniques that British industry had not previously encountered. New metallurgical testing procedures were developed to analyse German steel compositions and heat treatment processes that exceeded British experience. Precision measuring instruments capable of evaluating German dimensional accuracy standards were procured to support comprehensive component analysis. ballistic testing ranges were modified to accommodate systematic evaluation of German armour effectiveness under controlled conditions. The expansion of British testing capabilities reflected recognition that future captured equipment analysis would require technical sophistication matching German engineering achievements. The investment in advanced analytical equipment demonstrated British acknowledgement that their previous approaches to enemy technology assessment had been inadequate for evaluating superior German systems. The documentation procedures established for Tiger 131 examination created comprehensive technical records that influenced British approaches to technology assessment for decades afterward. Every component required detailed photographic documentation before disassembly to preserve evidence of German manufacturing techniques. Systematic measurement protocols were established to record dimensional characteristics that revealed German precision manufacturing capabilities. Chemical analysis procedures were developed to identify German alloy compositions and material treatments that exceeded British experience. Assembly drawings were created to document German engineering solutions that British designers had not considered. The meticulous documentation reflected British recognition that they were examining technology that represented significant advances over their own capabilities. The comprehensive records created during Tiger 131 analysis became foundational references for British tank development programs throughout the remainder of the war and well into the post-war period. The Tiger tank that had arrived at Point 1854 as an abandoned piece of battlefield wreckage had become something far more significant through 2 years of systematic British examination. The comprehensive analysis had forced British engineers to confront an uncomfortable truth that would reshape Allied understanding of technological warfare. German engineering had achieved advances across multiple disciplines simultaneously, creating weapons systems that exceeded British capabilities by margins that could not be overcome through incremental improvements or increased production volumes. The acknowledgement that enemy technology surpassed their own represented more than professional humility. It marked a fundamental transformation in how Britain approached industrial development, scientific research, and military procurement that would influence the nation's technical priorities for decades beyond the immediate wartime emergency. Tiger 131 had taught British engineers that excellence in warfare required not just courage and determination, but technological superiority that could only be achieved through systematic innovation and uncompromising standards.